In the final lecture for this section, I'll discuss passive pressure. Passive pressure refers to the passive resistance of a soil wedge. If you remember back to our earth pressure lectures, this is the pressure exerted by a soil wedge that is being compressed, similar to how active pressure from the soil wedge behind the anchor contributes to abutment sliding. Passive pressure from the soil wedge in front of the foundation could be engaged if the entire abutment started sliding. Now, if you remember this graphic from the ramp wall design lectures, theoretically there should be a zero force at the front of foundation. But if this is not the case, we then would begin to engage our passive pressure of the soil wedge in the front because we are starting to compress that soil. It is common practice in retaining wall design to avoid using passive pressure unless a shear key is specifically designed to engage a larger chunk of soil. Therefore, this lecture is solely to show you the process, but does not recommend using passive pressure as a key component for your design, or a component for your design at all. Now, the graphic here shows the soil wedge contributing to passive pressure superimposed on an example situation from a suspended bridge design. Here, alpha is the failure plane angle, and beta is the angle from the horizontal, which is the slope in front of the abutment. Using the slope geometry, we can calculate our passive pressure with the following equation, where h is the foundation embedment depth. We'll conservatively remove the top 30 centimeters of soil to account for disturbances during construction, and we don't want to assume this is properly compacted. So we get an h value of 0.7 meters for a standard bridge, which just comes from the fact that we have 1 meter embedment of our foundation minus 30 centimeters. However, before moving on, it is important to use some engineering judgment here. If the passive pressure is relying on a soil wedge, shouldn't that be reduced as the soil slopes away from the foundation? The answer is yes, and we can look at this in two different ways. Option one would be to just reduce our passive pressure coefficient. First, we can use the full equation to calculate our passive pressure coefficient, and if you want to try calculating Kp on your own, you can play with that beta value as a negative slope, changing it from -5 to -10 or even -30. How drastically does the passive pressure coefficient reduce? Well, for a 10-degree slope, or for a -5-degree slope down to a -10-degree slope, this reduces from a value of 3 to 2.77. And if we considered a 1 meter deep foundation, embedded 1 meter with an H of 0.7 meters, we get a passive pressure value of 12 kilonewtons per meter of wall. Now, the other option is to use charts from prescriptive codes or prescriptive documents like the NAVFAC in Chapter 7 is where I've grabbed this information. And all of this information is based off empirical testing, empirical values that we can use to read a passive pressure coefficient. And most research comparing empirical results to those calculated by the Rankine coefficients like above, we see that it's really not a good match for calculating the passive pressure of sloping backfill, so it is better to read off the chart. So first, there's a diagram of the situation we're looking at, and then in figure 7.2 of the NAVFAC Chapter 7 for granular soils, we can go in and read the Kp value based on our conditions for angle of internal friction and our backfill angle. That gives us a Kp value of 2.2, which we can go back and calculate a passive pressure of about 9.5 kilonewtons per meter of wall, which is significantly less than our value of 12 and probably a more realistic value that we'd want to be using.